whoops, this probably should be in the same video as the previous. Worth noting very quickly is that convolution and max pooling do have an inverse operation, that is the convo transpose and upsampling. I have used both of those down here. I'm not going to spend a huge amount of time going into what these look like inside. These are going to be important because when we build an autoencoder, which is basically what this is, right? This is essentially a little convolutional autoencoder. It is going to be important that the output layer and the input layer are the same size. Okay? And so, and so I have used a convolution, an activation, and a max pool, and then I've kind of wound them back with an upsample of the same size and a convo transpose of the same size to get an output that is the same size as my input. Notice that this actually wouldn't have worked out if I had used a 4x4 convolution, because if I used a 4x4 convolution, then that second layer would have size 28 minus 4 minus 1, or 25 by 25, right? And when I max pooled it, the edge would get shaved off, and you would go down to 12 by 12. Upsampling would multiply it by 2, so you'd go to 24 by 24, see where the problem is. And then the convo 2D transpose would get you to 27 by 27. Okay? Oh, whoops, and I think that actually should be a 1. I think that should be a 1. Right? And this would not work. Right? So if you know that you intend to perform a reverse transpose, you might have to either pick the size of your convolutions carefully or have the inverse operations not be the same size as the inputs. Now, not being the same size as the input doesn't actually kill you, right? Even when we talk about autoencoders, there actually is no rule that says that the lower half has to be the exact mirror of the upper half, right? Although it might be easier for you to keep track of if they are fairly close. I think my cat is trying to eat the format. Stop that. It's not. Kitty hates diet. Okay. So how do I know those are the same size? You actually don't have to take my word for it, because we actually can look at a summary, right? And that leads me to the fact that there are a couple of functions that I really should have mentioned before that it just sort of slipped my mind. These are not interesting functions to me because they're not fascinating models or theoretically interesting or anything. But if you want to actually use these kind of things, I really do have to tell you about them. So you can look at a model with model.summary. That gives you a very nice list of all of your layers and sizes. You can save a model with model.save. Here, because I gave it the H5 suffix, it will be in HDF5 format, which I believe in theory is a cross-platform standard. So I think that this model, in theory, could be loadable by like a PyTorch user, right? In practice, I don't know how well that works. I would not be surprised if Google did something weird and janky with their H5 implementation. I would not be surprised if like the PyTorch H5 loader sometimes doesn't work right. I haven't tried it, so I can't tell you. My limited experience with Google and TensorFlow leads me to not put a lot of trust in their ability to follow a standard, but that's just me guessing. In any case, in theory, H5 is a standard format, and this might be portable. So you can load a model with keras.models.load model, boink, with that path, which just returns to you another model object. You can evaluate a model with test. Why do we care when you can call a model on an item? Remember that they're callable? Well, test here can be a data set, which means that it can have both X and label, which means that this can evaluate will figure out how well the model does and give you a loss, right? Whereas model called on an item without a label just gives you the output. And finally, we actually can, damn it, that's just LibreOffice, should be lowercase p. LibreOffice helpfully capitalized the first word on the line. we actually can look into our model and get access to the layers, right? So if you want to know what the output shape of a layer is, or what its kernel looks like, or adjust its weights, or do a whole bunch of stuff, you actually can just write model.layers with an index, and then you can start looking at members on those layers. Bear in mind, those layers are objects of different types, so they may have different members, right? Some of them have, I think they should all have an output shape. I think that one they should all have. Some others they may not all have, right? Different models of different types may have different members. All right, that is the end of the slides, but I do have a code sample we can use.